All right, well, we're into chapter 1 in the thick of things, and we're going to be here for a while. Piping systems, true? Were you able to turn in this homework? And did you email it like I asked? UTSA Thermo? So let's press forward here. So we're dealing with piping systems. Essentially, you have a review of fluid mechanics, but putting it together is more challenging, or probably we have to do it more in depth than what you were exposed to in fluid mechanics. So in fluid mechanics, you were exposed to major losses in a piping system. That's an old terminology, the major. It doesn't mean that it's the most important. It just means that it's for straight runs of pipe. And so the head loss at a straight run of pipe, you calculate by having a friction factor. That friction factor is a function of the relative roughness and the Reynolds number. Either one, doesn't matter which one comes first. It's a function of those two things. Often you can get it graphically using the Moody diagram. Or I encourage you to do there's a number of them, but the Churchill equation that's in the textbook. I showed how to get some add-in software. University of Alabama, download it. Then you don't have to build it. You could just use it, as well as you could recode it. You could code it up. How many people coded it up themselves? How many people went and looked at and downloaded the add-in? So, any problems with the add-ins that you downloaded? It's okay. I mean, there's not a lot in it. I mean, it's not as extensive as the thermo download, but it's helpful. Okay, so we have the friction factor. Then we multiply by a dimensionless length to length, one length to another length. The length of the pipe divided by the diameter. So how many diameters? It's basically a measure of how long it is compared to the diameter. And then the last, what do you multiply by? Well, there's three choices out there. If you want to talk about pressure loss, you multiply by, maybe I should have written it a different way here. You have like three losses. You could express it as a pressure loss, a head loss, or a head loss. Now, I know that I like to use a cap HL to distinguish between energy per unit mass and the lowercase h per energy per unit weight. Energy per unit weight. But the book doesn't, and so you just have to pay attention. Lowercase h could be energy per unit mass. Most of the time it is. The book says in chapter 1 that's what they're going to treat it as, lowercase h. But sometimes you'll turn the page and it'll be in feet, and you're going, hey, that's not energy per unit mass. That's energy per unit weight, feet. And so that's the other head, the more traditional head. And then the pressure we like to interpret as energy per unit volume. So what you do is you multiply right here by either a velocity pressure or velocity head in energy per unit mass, or velocity head in elevation or energy per unit weight. Flush this out in more detail for me, Professor. Well, this would be 1/2 rho v squared. This one would be, what would it be? B squared over 2, or 1/2 v squared. And the last one is b squared over 2g. All you did was what we talked about before. Usually we think about starting Bernoulli's equation in the form of pressure. Then we divide by density. Divide by density, or multiply by 1 over rho. Multiply by 1 over rho. There you go. You went from pressure to another form of some conservation of energy statement, basically from energy per unit volume to energy per unit mass. And then if you went and divided by 1 over rho g, you went from energy per unit volume to energy per unit weight. And that has the units, it helps you if you just remember the typical SI or USCS units. Okay, SI, you can do both of them. So for this last form, the SI would be in, meters in SI or feet in USCS. And then this one would be maybe, I don't know, either you do meter squared per second squared, which can be converted to kilojoules per kilogram or joules per kilogram. Either one works. You know, you have to just do the conversion. Or it can be in foot-pound force per pound mass. Isn't foot-pound force a good energy, mechanical energy, in United States Customer System units? Let's leave it at that for the USCS, but you could also do foot squared per second squared, which is similar. It's just like in the SI. You know, meter squared per second squared can be converted to kilojoules per kilogram, and foot squared per second squared can be converted to foot-pound force per pound mass. And then for the pressure, a lot of this is more familiar. We're comfortable with that. We would talk about pound force per inch squared, often abbreviated PSI, pound force per inch squared. Or you'll also see pound force per foot squared. It's just, it's pressure. It's force per unit area. And then over here, we typically are in pascals or kilopascals or some pressure. Okay, so now let's talk about minor. That's a little review of where we were last time. What does it mean about minor? It means the loss coefficients or the losses due to friction that are not associated with straight runs. That's everything else. Everything else. Where do you have a loss? Where do you have frictional loss of mechanical energy? Where is it going to go to? It's going to go to thermal energy. Just make the fluid a little warmer and dissipate it. So this is things like if you have a valve in a piping system, the valve introduces some obstruction. Maybe when it's fully open, it's not much of an obstruction. Maybe when it's partially closed, it's a big obstruction. So it introduces some loss. Maybe you have something to change the direction of the flow. Easiest one is an elbow. So the flow is coming this way, and you turn it and you bring it out that way. That's a 90-degree elbow. They have a lot of different 90-degree elbows. Short radius, standard radius, long radius. A lot of loss coefficients, a lot of ways to predict that loss in that fitting, that minor loss due to the presence of an elbow. All right, maybe you have an entrance into a pipe. So I have a tank, it's full of fluid, and then I have a pipe. And that fluid right here is whoops, I wanted to change color, is going into that. It's an entrance loss coefficient. That entrance loss will be different if it's sharp-edged, flush, which is very, very common, or if the tank, maybe it's like this, and you have protruding into the tank, you would think, what's the difference there? It's a different loss coefficient. All right? Or if I have a tank and I have kind of a curved, smooth entrance into the pipe. So you try to put a little radius. Instead of having a sharp edge, it's a very smooth edge into the pipe. And then there's another one that's worth discussing, and it's the not an entrance, but an exit. And so if I have fluid flow in a pipe and it's coming and I need to push it into a tank, I dump it into a tank. In that tank, the fluid at the discharge of that pipe is submerged. It's submerged, then there's a loss coefficient for it. Okay? There's a loss coefficient for a submerged outlet of a pipe into a tank. There's other ones. These are some big ones. Anybody remember one? Sudden contraction, sudden expansion, those. maybe more of not a sudden but a gradual contraction and a gradual expansion. Those changing diameters of pipe will introduce losses. Anybody else remember any loss coefficient? Diverging, yeah, that'd be changing the diameter. So we're kind of going in a pipe, long pipe, and yet we're having to, oh, that's right, split like T's and Y's, yeah. And so you have loss coefficients. It can get a little complicated on those. Okay, here's a question for you. I had talked about this entrance into from the tank into the pipe. The flow's going that way, the flow's going that way, the flow's going that way. I have introduced case A, case B, and case C. I'd like one volunteer to describe, just repeat the words I used. What is case A? Sharp-edged, is submerged entrance from a tank into it. And it's either flush or it's flush. It's flush, sharp-edged. Okay. How about case B? Protruding. How about the edge? No, it's just a pipe stuck in. Actually, that can be quite common that they build it that way. Okay. And then the case C. It's flush, but it's curved entrance. It's not sharp-edged entrance. Now, what we're going to do, the model, the minor losses is you take and you say the head loss, and I could put it in three different forms, just like we talked about right here for the major head loss, is equal to a loss coefficient times some velocity pressure or velocity head, I'll put a cap H, velocity, or some other velocity head. All times some velocity head or something like that, okay? Professor, is this velocity head the same as what you had up here, the 1/2 rho v squared, if I'm dealing with pressure? Yes, it is. Is this cap H, is that energy per unit mass, is that going to be the v squared over 2? Yep, that sure is. And would this be the v squared over 2g? Yes, it is. So when you look at the major loss, this part right here is the same. But instead of multiplying a loss coefficient k for the minor losses, you multiply FL over D for the major losses. That's the only difference. See that? And so then these are the either energy per unit volume, energy per unit mass, energy per unit weight. Either you talk about a pressure loss or a head loss in energy per unit mass or a head loss in energy per unit weight. Same units. It's that I just put up there. In the U.S. customary system units, PSI or foot squared per second squared or foot, something like that. Okay. So really, the coefficient that's new is just this loss coefficient. Many books have it as a K for a loss coefficient. If you said, oh, I can't use K for my loss coefficient and I want one letter to represent the loss coefficient, what one letter would you pick? You can't use K for some odd reason. What letter would you put for the loss coefficient? C. You may see C every now and then, okay? Or some other value, right? All right, but now, let's go back to this entrance, because it's common that we have pipe flow, we have to get it into the pipe and get it started. Which one has a greater K? If you have a larger K, magnitude of K, don't you have a greater loss for the same rate of flow in the pipe? So yeah, same velocity in the pipe, same rate of speed of flow in the pipe, same velocity pressure or head pressure or velocity head. Okay, so which one has a larger K? Case A, B, or C? B. Congratulations. It's very, very good. How about which one has the lowest K?
C.
C. You're absolutely right. And for those that missed both of those, which one is in the middle? All right. So you have to pay attention. When I teach the fluids, I usually talk about just follow a little pack of fluid and say, I'm going to be here and I'm going to go in here. It's easy, go straight in, but you have to bend around here, and that sharp edge is sometimes has a little recirculation region. That's why it's a larger loss than if it's smooth to help make that turn. Just think about little fluid packets. But when you come here, you got some fluid packet here that eventually is going to have a really wild turn. And so the probability of having a greater degree of separation, hence more loss for the protruding pipe, is why you have a larger loss coefficient. Okay, elbows and valves. The valve K depends on where it's at. Is it fully open, what type of valve it is, and or what degree of closure on it. Okay. So we just talked about the tank entrance, the elbow, the valve, and a submerged pipe. What's submerged? The outlet of the pipe that goes into the tank. If I have a pipe and I'm using it to fill this tank, and yet the end of the pipe is here, and this is the tank right here, and the fluid level in the tank's there, and the water shooting out, is there a loss coefficient associated with coming out of that pipe? No, there's not. No, there's not. Okay. Okay. We can develop examples when you'll see that. Yes, sir.
Is it just because of the density of air relative to the...
No, it's because you end your Bernoulli line right there. And because you end it there, the exit speed is not negligible. But if you have the other case where you have the pipe into a tank and the outlet of the pipe is submerged, you don't end your Bernoulli here, you extend it all the way to there. What is the speed at that point? 0. So basically the loss coefficient accounts for the kinetic energy of the flow coming out that is dissipated. That's exactly what it is. And the loss coefficient for this submerged is 1. Submerged exit. Okay, so let me ask this. Would it matter if the submerged exit had a very smooth sort of, I'm trying to draw a smooth discharge into the tank, or a very sharp edge discharge into the tank, or protruding into the tank? And I have the fluid level, it's submerged, it's submerged, it's submerged. Do these have different loss coefficients? They do not. They do not. They all have K of 1, because what you're doing is you're taking that Bernoulli and going from here, from there, to there, and all of that kinetic energy that was in the pipe before it tried to get out of the pipe is going to be dissipated. And that's why the loss coefficient's 1 for all those cases. Either this is a very stellar class, or I'm talking to just a handful of very stellar students who really grasp that. That is a difficult concept. Yes?
So the one on the top is K equals 0 in this case? Or?
The one on the top right here, that's right. What you do is...
the one below.
Yeah, this one has no loss. That's right, no loss. No loss, but you end here. That's where you need to end the application of the Bernoulli. Because once you start to come out into a free jet and you're falling, those assumptions about inviscid flow, the air is breaking it up, is gone. Yes?
What if the fluid was a gas? Is it zero?
No. No, because you're discharging into the same fluid. So if you're discharging the same fluid, it's really gas into a gas. It's submerged. All that kinetic energy is going to be dissipated. What you'd have to do is, if your pipe is like this and you're discharging into a tank of air, you're going to take your Bernoulli and end it out here somewhere where it's at rest. The air is at rest. And so when you come across, all that's going to be dissipated. Put a loss coefficient associated with 1. Or I don't see it being a big difference if you maybe end it right there in air. Yes, sir?
So with the loss coefficient of 1, your minor loss plus your major loss would be 2 times the major loss.
Could be, yeah. And so you just step through, and we're going to solve a problem where you have to just do the bookkeeping. Just do the bookkeeping. Need to talk about power. We talked about it last time. There's 3 types of power you need to get straight in your mind. Think about a pipe and think about liquids. It's a little easier that way, and I have a pump. And what is the purpose of the pump? The pump's purpose is to boost the pressure across the pump, right? Across this pump, there needs to be a pressure increase. If I have the same fluid, it's not compressible. I'm talking a compressor. It's not changing temperature, it's not changing density, and the pipe diameters aren't changing. Did the kinetic energy of the flow change in and out? No. So the kinetic energy is not changing across a pump. And how about the elevation across a pump? No, it's negligible. The pumps are small, compact little things. Okay, so basically the pump's purpose is to change the pressure of the fluid. So we now know that this pressure is interpreted as energy per unit. I forgot. Energy per unit. Pressure is energy per unit what? Volume. Energy per unit volume. If I multiply that by volume per unit time, don't I get energy per unit time? The volumes cancel. What is energy per unit time? Power. Watts. Exactly. So if I take and I say I want to know how much energy is mechanical energy, getting into the fluid by the pump. The pump's purpose is to boost the mechanical energy of the fluid. I would just say that fluid power, W dot fluid, for lack of better things, is a symbol for that. The power getting into the fluid is the pressure gain. Let me just write it. I could put it like pressure gain in the fluid across the pump times the volumetric flow rate of the fluid through the pump. Does that make sense? You can go back to Thermal 1 and verify that equation. I may have done a quick derivation of that to remind you. You can go back to fluids and peel back, and I encourage you to do that. You didn't throw your book away, you didn't sell it, you saved it so you could refer to it. And so there you go. But what do you do to feed the pump in order to achieve the boosting of the pressure, increasing the mechanical energy of the fluid going through the pump? You had to feed it shaft power. That's the purpose. So a device known as a pump was fed shaft power, W dot SH, shaft, or, okay, AFT. Let me ask you this. How does the shaft power, 20 kilowatts, compare to the fluid power? 20 kilowatts, less than 20 kilowatts, greater than kilowatt? Which is greater? The shaft power. So you might say, hey, I have 20 kilowatts coming in and only 18 are going to where I want it to go. That'll boost the pressure of the flow, to boost mechanical energy of the flow. The only way it's going to be realized if it's incompressible, no elevation change, no kinetic energy change, is through the pressure change. Where did the 2 kilowatts go? Off in heat, viscous dissipation, something like that. Energy is definitely conserved, but the mechanical 20 kilowatts only went to the mechanical 18 kilowatts. 2 came out of the mechanical conservation of energy in viscous dissipation. And it's out of our bookkeeping. It's somewhere else. So guess what? The efficiency of the pump can be, it's where the power that I wanted to get into the fluid divided by how much I had to feed the shaft to the pump. You back it up. You say, what supplies shaft power to most of the pumps around here? Electric motor. So here's my rendition of electric motor. What do you feed the electric motor, plus and minus? You feed it W dot ELEC. What does ELEC stand for? Electric power. Electric power, right? Very simply, you would just, if it's no motors are like this, but if it's just a single phase and you have no phase lag or anything, then it's just the RMS product of the voltage and the RMS times the RMS current. But if you do have 3-phase and you have, what is it, square root of 3 over 2, and then if you have a power factor, a lag between the voltage and the current, then you have a power factor term in that power calculation. So it's a little bit of work, but in principle, it's just the electric power. And CPS is selling electric power. You're going to have to pay for that. Okay? So we don't have 100% conversion of the electricity into that motor shaft that drives the pump, so we have the efficiency of the motor. What is it? W dot shaft divided by W dot electric that's supplied to the motor. So we could back up these efficiencies. We're going to use this concept in a second. Remember how to calculate the Moody diagram. We use it a lot, but once we get into Excel, then we just use it to check our values. You should check the values as much as you can in your calculations in Excel. This problem you sent it to me. I think most people did send it to the right email, but this is the right email, okay? It goes to utsathermo@gmail.com, not armonteufel@utsa.edu. All right? And very good on the subject line. And how many people scanned it and just attached it and didn't put their work in a pile? Very good. Maybe we'll require it. How many people, if I said you must do it that way and don't turn in paper, would be really upset because it would be hard for them to scan it? One? No. Maybe they're shy. Your friends are shy. Nobody else? Because I sure would like to do that. But I don't know if we'll do it. Yes, you would be hard pressed?
Oh, no. You just use the scanners from the library. You don't take that over.
You have some friends that'll probably help you a little bit, and then you're going to be brought into the world of 2016. 2016. I know I still live in about 1980. Yes, sir.
Is there a deadline for it, like last time?
Okay, okay. If you haven't turned it in, we're a little lax here. Turn it in. Midnight tonight or tomorrow sometime. I mean, it's a hard thing to get started in the semester, isn't it? You're juggling the books, trying to find the classroom, but but we need to. But this is the due date for the homeworks, and later in the semester we'll be real tight on it, and you need to get it in by the time of the start of class. I'm really leaning toward electronic submission, so I like that. Thank you. Okay, let's go. Continue on. Let's solve this problem. A 10,000 foot long pipe. What a log pipe. No, long, L-O-N-G. Sorry about that. L-O-N-G. Forgot the N in there. Pipe feeds a hydraulic turbine. So water's going to go through this pipe, and then it's going to go through the turbine, and the turbine's going to extract some energy out of the pipe, out of the water. The required flow rate to the turbine, they want 2,000 GPM of water flowing through the pipe. The head loss should be less than 100 foot-pound force per pound mass. So you don't want all the frictional head loss to eat up the possible power that the hydraulic turbine would then convert, and maybe you're selling electricity. So maybe somebody said, look, keep the head loss in this 2,000 or 10,000 foot long pipe that needs to supply 2,000 GPM. Keep it less than 100. Does that make sense? It's like, don't go over my budget. My budget here's some money. Go have a party, but don't spend more than the money I give you. Right? Something like that. Don't go over 100 foot-pound force per pound mass. Is that a good measure of head loss? And what type of head loss are we talking? Energy per unit volume, energy per unit mass, or energy per unit weight? Which one is it? It's energy per unit mass. You're getting very good at this. You're getting very good at this. That's great. And so the pipe is going to be a Schedule 40 commercial steel. You don't know much about pipe, you can turn to the appendix in the back of the book. In the appendix, I think C has ANSI pipe information. So you look at appendix C in the back of the book. They go Schedule 10, Schedule 20, Schedule 30. Pretty much everything in the world is Schedule 40. It's standard pipe scheduling. But if you want, you can buy a Schedule 80. Schedule 80 is an extra heavy pipe, thick-walled. It can handle higher pressures. And if you work in a nuclear reactor or whatever, you can really get some thick pipes. And so I don't know the maximum here is Schedule 80. They have a Schedule 100. They have a Schedule 120, a Schedule 140, Schedule 160. What are they doing? Thick walls, boosting it. How many people have handled pipe and know that about schedules? Whatever. There you go. It's kind of nice. Schedule 40 just is a standard. I don't know if Home Depot, Lowe's, or all those places, if you can even buy anything more substantial. You have to really go to a pipe supply that really, okay, give me this scheduled pipe. Okay, a gate valve is used for flow control. Now, a gate valve, it's just what it sounds. I have a pipe, I have something that slides up and down, and it's a gate. Chunk, chunk. Gate valves, they can shut it off, and they can open it up. And do you think a gate valve is good to throttle the flow with? Probably not. It's probably just to open it and close it, like an isolation valve. That would be a gate valve. And so you say, I'm going to have to model that gate valve. You can look in a table in the chapter 1, and you can get it both the image of the gate valve as well as loss values, loss coefficients for the gate valve. So take a look at figure 1.8. There's a number of sketches. Excellent. They copied it out of the Crane's manual. I should have brought that. I thought I was going to do that today and let it pass it around. You can see the Crane manual for that. Or if you look in the table TABLE 1-1, you can find the gate valve fully open has a loss coefficient of 0.17 when it's 3/4 open. So this is 100% open. When it's 3/4 open, well, the loss coefficient, what do you think? Is it going to change? What's it going to do? Go up? It goes up, and so it goes to 0.9. Then they have it 1/2 open, and the valve goes to, there's a typo in the book, 4.5. It doesn't go to 45. If you have a book, look for a missing decimal right there, okay? And then when it's 1/4 open, then it's 24. See, it wouldn't make sense if it went 0.9 to 45, then to 24. Make sense? It's 4.5. So typo, TYPO. Got it. Okay. Determine the minimum pipe diameter. Part A, let's just focus on part A. What do you mean minimum pipe diameter? You don't want the head loss to be more than that. Okay? Did they give me any information graphically or anything about any minor loss coefficient other than the gate valve? It's only one minor loss coefficient gate valve and the major loss of the straight run pipe of known length. So what you can do is maybe, you probably want to do Bernoulli. Start here, you have a straight run, put a valve in it that's controllable, and there's the end. So 1 to 2. They didn't tell me about the entrance to 1 or the exit to 2 or anything like that, right? And they said the H loss needs to be less than the 100 foot-pound force per pound mass. Okay. Well, so what is my head loss? It's going to be the head loss due to the straight. You can make these subscripts shorter, but when I usually make subscripts long until I'm comfortable, then I shorten them. It's a major loss. Plus the head loss for the valve. How do I model the head loss? Well, F L over D plus K times the H velocity, the velocity head. Because these are in those units, that head velocity is going to be v squared divided by 2. Just v squared divided by 2. Okay. But the problem is, to calculate the velocity, in order to get the velocity head, and to get the friction factor, I need the Reynolds number. I need to know the speed of the flow in the pipe. But it's one of these chicken and egg things. right? So guess what engineers have to do? Iterate. Computers make it a little easier. So the minimum pipe diameter, I'm going to pick a pipe diameter, and I'm going to see if it works. I'm going to see if it calculates a head loss that's less than the 100 that I need. And if it is, maybe I can get a smaller diameter. If it's not, I need to get a bigger diameter, redo the calculation. So here we go. We're just going to flip a coin because I have no idea how big this pipe should be. Somebody throw out a number. 10 inch. 10 inch pipe. So we're going to grab a 10 inch diameter of 10 inch. Now, one of the things that you should do is you should go back and look at this Appendix C. If somebody says, I want an 11-inch pipe. Take a walk. You ain't getting it. You're not going to buy it in San Antonio. It's not out there. I want 10.33-inch pipe. No, no, no. Engineers, this is it. We got to conform. You can buy a 10-inch pipe, 12-inch pipe, 14-inch pipe. But then they start skipping, you know, it's like every 2 inches. But they used to have lots finer, you know, like you can get a 1-inch, 1.5-inch pipe, 2-inch pipe. But then as they get larger, it's like you can't make all these sizes and store them and stock them. So there you go. So 10-inch pipe. So we're going to do this. Once I pick the pipe diameter, I can basically get the speed in the pipe by having the volumetric flow rate and divide by the area. True? That volumetric flow rate, the AV is 2,000 gallons. Then I have to convert my gallons to cubic foot. It's possible. 0.1336 something, yeah, cubic foot per gallon. So make that conversion, and then I got to convert my minutes to seconds, and so I'll get this converted over to so many cubic feet per second, and then I'll divide by the area in foot squared, and I'll get my speed in foot per second. True? Didn't lose anybody. Once I have that, then I can get my velocity head, no problem. But if my velocity head is in units of foot squared per second squared, I need to multiply by a conversion factor, just like we used a conversion factor to go from gallons to cubic foot and minutes to seconds. That conversion factor is, hey, you know what? I forgot. I was going to ask you that question last time, wasn't I? Let me back up here. Insert new page. Last time I was talking about this term, G. What is G? Acceleration due to Earth's gravity. You let things go, they fall. Most applications, engineers aren't letting things go and they're not falling. They have weight. And so, basically, you think about G. Remember I had this table? And I said in the SI and in the USCS, if the thing is free falling or if it's just sitting. Okay, can't spell, sorry. If it's just sitting there, got it? It's not. It's stationary. I said, if it's falling, G is 9.81 meters per second squared. You got that so ingrained in your memory. G is equal to 32.2 foot per second squared. But when it's just sitting, think about this equation. The weight is equal to the mass times G. Hence, G is simply the weight divided by the mass. So, we worked it out last time that G was 9.81 newtons per kilogram. Was that magic? Did he pull a rabbit out of a hat? No, it's easy. Do you want me to show you again? But I left off and I said, what is G over here? What is the weight per unit mass? And I want one volunteer. Should I pick a row? First, second, third, fourth? Which row should volunteer? Third row. 1, 2, 3. It's heavily populated. There's not an empty seat in the third row. You're in the third. Jeff, you're in the third row. What is G?
1 pound force per minute, 1 pound mass.
I'm sorry?
Apparently I was told not to say it.
Okay, they told you not to say it, but he wants to shine, then he knows it. What is it? Only third row. All right, I'm going to have to go to another row, but I'm not going to go to the second row. I'm going to skip to the fifth row. The fifth row is a bunch of sleep. He's texting on me. What is it? Oh, you were using your calculator doing the conversion quick. Sorry, you weren't texting. What is it, fifth row? Okay, how did I do this one right here? I started with 9.81 meters per second squared, and I didn't violate any rules. And I said, I'm going to multiply by a kilogram over a kilogram, or forget that even, just do it this way. What's a Newton? A Newton is a kilogram meter per second squared. There you go. So you just have to do the same thing here. G is equal to 32.2 foot per second squared. I need to multiply by 1. I need to multiply by a great unit conversion factor. The great unit conversion factor is 1 pound mass at the surface of the Earth. If you let it fall, we'll experience 32.2 foot per second squared of acceleration, and 1 pound mass put on the surface of the Earth of a scale will register 1 pound force weight. Hence, we get rid of the foot, we get rid of the second squared, we get rid of the 32. What? Hey, I know that's what you said, didn't you? You were right. I like conversion factors of 1. I can remember them. And so this is the easy one. Somebody says, I stepped on the scale, and this morning I weighed 190 pounds. That's my weight. It's a pound force. Somebody says, yeah, but I want to know your mass. No problem. 190 pounds. LBM. True? I don't know why we want to move away from this system of units. I know we do. 5280 and 12 and a bunch of other things. What's a yard? 36 inches. Anyway, we're getting rid of it. But it's SI is nice because everything's in factors of 10 and hundreds and thousands. And here is one of these examples where let's not forget it's really, really easy. Surface of the Earth, the weight of an object that has a mass of 1 pound is 1 pound. 1 pound mass has a weight of 1 pound force. This is probably the most easy, and yet somehow in our whole engineering curriculum, student group after student group after student group, professor, you're talking Greek to me. I don't understand this. This is easy. This is easy. True? True. So what we have to do is we multiply to get the right units. The unit conversion factor is the same one I just used. A pound mass at 32.2 foot per second squared is a pound force. Is that one? What in the blue? Is that just unity? Yeah, that's what it is. And so then we go one of the feet go, and we get seconds go, and we're left with the information that I want. I want the velocity head in foot pound force per pound mass. And now it's energy per unit mass in some very convenient units. All right. Now let's continue on. So we get the velocity head. We got the loss coefficient for this valve. We have to get the friction factor. To get the friction factor, I got to get the Reynolds number. The Reynolds number is rho VD over mu, or VD over nu. Either one. You look up for water. Water, they didn't tell you the temperature. Grab it at 60 degrees F is a good one. And what value did I grab? 1.22 times 10 to the minus 5 foot squared per second. Does that look like a good foot squared per second? Are those reasonable units for my viscosity? Is that an absolute or kinematic viscosity, Professor? Absolute or kinematic? Kinematic. You're absolutely correct. Very good. And then, once you have that Reynolds number, you get the type of pipe it is. What type of pipe is it? It's a commercial steel pipe. How many people can get me the relative the roughness of a commercial steel pipe. What is the roughness? It's in our textbook. It's kind of hidden. I'm going to show you where to get it. You get it off of figure 1.5, 1-5. And what you have to do is turn sideways and read the numbers on the line. All right? And so I have to do that myself. So for commercial steel, 0.00015. 0.00015. What are the units on that? Feet. You're absolutely correct. They're in units of feet. Very good. So it's not all those numbers are not labeled. You just have to know, oh, it's feet. Yes, sir.
Is that roughness on the Excel sheet or the Excel add-on that we downloaded?
I don't think you have to use it. So you calculate the relative roughness, take that roughness and divide by the diameter. And now you have a relative roughness. That's what goes into the Churchill equation.
But I was just wondering if that chart was coded into...
I don't think so. I think...
Just like the Moody chart was.
Right. I don't think so. And so then you get the friction factor as a function of the Reynolds number and relative roughness. Okay. Now, once I have the friction factor, I come over, I got the length, the diameter, the K, I add them up, I multiply by the velocity head, I see whether or not it's greater than 100 or less than 100, and away I go. You have to do things by hand, and then we do it by Excel. Ready to do it by Excel? Or I have another option for you. Well, I should do it by Excel. So I would build an Excel file like this, and the mouse is going to come alive. What was our gallons per minute? 2,000. How do you go from 2,000 gallons per minute to cubic feet per second? Take your 2,000 and you multiply by 0.1, what was it, 33681, and that's going to be how many cubic feet per minute. And a minute is 60 seconds, and there it is. This is the volumetric flow rate in feet. What was our length? Pi. Oh, forget it. I already solved it. Let's quit. Okay, quit that. There. Did you guess I solved it before? So anyway, the GPM, and then this is the equation for that. I put the length there. Head available is what I'm going to check it against. There's that epsilon in feet. Is that the same value that we read off? 0.00015? Yeah. The loss coefficient for a very three-quarter close, but if it's 0.17 is for the, 0.17 is the loss coefficient. Our viscosity and our density of water we type in, we assume, what did we say, a 10-inch? So we start with a 10, there's our diameter in inches, or feet, our area in feet, our velocity now. You can see the equation C3 divided by C12. And then just to make it so it's more visible, I pushed it over, and then you get the velocity head. Notice I put it in two lines. This velocity head in foot squared per second squared. And then I even show you right here, this is the equation used to convert to the foot-pound force per pound mass. And then you get the Reynolds number, VD over nu. There it is. It's turbulent flow. There's the relative roughness. Use the Churchill equation to get the friction factor. Check it on the Moody diagram. 0.015 looks good. Calculate your major head loss in those units. What's the equation? F L over D times the velocity head. Then calculate the minor due to that fully opened gate valve. Notice that I sum them up and the total is 188.90. Well, 100% of it's due to the major. Nothing is due to that valve. See how I did the percentages over here on the side? That's because it's just like it's all due to, you can just look, it's all, the head loss is all due to the straight run. So this is not below 100, is it? So what do I have to do? Try 12. And now it's below. It's 75. Can I get a 9-inch pipe? Nope. So let's say I build it with the 12 and somehow there is 100 loss. What is my actual flow rate going to be? So what you can do is you could use GoalSeek, you can see that, to find the actual flow rate. If you built it and actually there was 100, what you have to do is you have to say the head available minus the loss, okay, it's equal to available minus what you actually lose. So I've got 24 more units of head loss that I could have. So what's the flow rate going to do if I install? That flow rate's not going to be 2,000, is it? So what you do is you say drive that cell to 0 using GoalSeek. Where do you find GoalSeek? Under Data tab, right up here. Under What If Analysis. And you say GoalSeek. Okay, if you've never used it, it says, okay, set what cell? And it's highlighting the cell I was in. Otherwise, you have to get to that cell. That cell is whatever, F10. You want to set that value to 0 by changing the flow rate to find out if you're going to have more than 2,000 GPM, but what is it? And it's 2,315 GPM. Cancel.
I have a question.
Yes.
About the diameter.
Yes.
So you said that we need to find the diameter that is within
In the tables, don't.
Is that a nominal? So the
Yes.
diameter is going to be a different size?
Oh, now that's a great question. I was going to cover that. If you look, the inner diameter and the nominal diameter are very close to each other, but they're not spot on. Because our flow rates was given to be 2,000 GPM, I didn't try to go in and say I'm going to select a 12-inch nominal diameter with the inner diameter for Schedule 40, but it's listed in this appendix. If somebody has appendix, maybe they can read it. I'll get to it right now. But it's an interesting thing to see exactly how big. The Schedule 40 pipe, 12-inch, 11.626.
So that's not going to change?
Not that much. You can put it in. We could do it right now. 11.626. Notice 75.7. You're still below 100. You're still below 100. You still go with the 12-inch, nominal 12. Now, if I go over here and I do the redo the GoalSeek, what if GoalSeek, and you set that. Unfortunately, you have to retype a lot of this stuff by changing that. It comes in at 2,130 compared to what it was just a minute ago. Now, that problem will require you to sort of explore different diameters and then look at the flow rates. Oh, it looks like I need at least a 12. A 14 is too big. And then the problem also asks you to say, what happens if you start closing that valve and I change the loss coefficient? Just rerun your code, grab that value and put it over. Later I can show you another Excel feature to do that more quickly, but don't worry about it. Do it by hand. Then you'll appreciate the acceleration. And then you plot it. What does this plot show you? The flow rate in GPM is a function of open valve, 3/4 open, half open, 1/4 open. We're going to get to that concept. It's really not covered in this book very well, or if at all. That valve doesn't have much authority over the system, but it's not supposed to. It's a gate valve. It's not a control valve. But we'll look, if I have time, at the valve authority. And when you buy valves to put in, if they're supposed to control, they need to have authority. Meaning, when they're even fully open, they're going to have a significant pressure loss across them. Because when they start to close, they need to really come on strong. We have one more problem, do we not? How many minutes do we have? 14 minutes. That person is tracking me. Well, this is a long problem, but it's your next problem that you turn in too. It's modified slightly. So I have a pump, and it's used to move so much flow rate, pounds per second, of a light oil, and the temperature of the oil is given so I can get the viscosity and density, through a 500-foot long, 2-inch ID, so forget about it's just 2-inch ID, cast iron pipe from a lower to a higher elevation. The elevation difference between the fluid levels in the tank is 25 feet. So the sketch is like this. There's the fluid level in the tank. And the next tank is like this with its fluid level in the tank. And the elevation difference between the two fluid levels is 25 foot. So you'd like to transfer it. Now, you grab a pipe, you bring it out, you put it through a pump. That's going to add the pressure. Do a bend, elbow, elbow, and then come and discharge. So that's the schematic. There's a flush, sharp-edged entrance to the pipe in the lower tank. I showed it protruding, my mistake. Sorry about that. Get rid of it. Now it's sharp. And so this loss coefficient for that guy, 0.5. You have a sharp-edged exit from the pipe in the upper tank. There's a loss. Maybe I should change the color of that. I kind of circle. Or I didn't change the color, did I? Change the color. And that loss coefficient's 1.0 because you're going to apply a Bernoulli to go from this point through the pump, through the two elbows, to that point. Got it? So you're going to go from point 1 to point 2. Let's continue to read. There are two 90-degree elbows, so watch out for the loss on those. Both of them have a K of 0.75. You can get those values out of the tables. You need to get those values out of the tables. It's a 90-degree standard elbow. The lower tank is sealed and pressurized. That's why I put a lid on it. The upper tank is open to the atmosphere. The air pressure above it right here is 5 psi-G. See that? 5 psi-G. Okay? The upper tank is open. So with this viscosity and density, and you're given efficiency of the pump and efficiency of the electric motor, determine the electric power required to run the pump. You want to solve as much of this before you get to Excel by hand. And when you do it with the Bernoulli's equation going from there to there, let's write it all out. I'll write it in terms of pressure because P1 is given, isn't it? 5 psi-G. P1 plus 1/2 rho V1 squared plus rho GZ1 plus any pressure gains in the system equal to P2 plus 1/2 rho V2 squared plus rho GZ2 plus any pressure losses. Is that a correct writing of this equation? This term for the pressure loss is going to have the pressure loss straight runs plus 2 times the pressure loss in elbows plus 1 times the pressure loss in an entrance plus 1 times the pressure loss in an exit. So those have to be added up. Now, let's talk a little bit about these terms. Is P1 0? No. But P1 minus P2, P2 you could think of as 0 gauge, or you could put P2 over on the other side, and P1 minus P2 is 5 psi gauge. All right. How about V1 such that 1/2 rho V1 squared is 0? Yeah, it's a large diameter tank. They don't give us any. That's why we started the Bernoulli at that interface. How about 1/2 rho V2 squared? Yeah. If you would have stopped it here at the discharge, you'd have to worry about the pressure at the discharge. You'd then have the kinetic energy at the discharge, but that's not what we have. Okay. So the pressure, let me just kind of rewrite this equation. The pressure that the gain from the pump is equal to the pressure loss due to the major and minors, all summed up, plus rho G Z2 minus Z1. I've got to push it uphill. I got to transfer it to a higher elevation. And that higher elevation is right here, 25 foot. It's H, cap H, isn't it? And then there's one other term, and you bring this P1 over, it's minus P1. Why is there a minus? Keep track of the minuses and pluses, but having a pressurized lower tank helps push it up. So that 5 psi G is helping it go. So that's helpful, true? I think once you get that, then you said, hey, I've done these loss coefficients before. It's pretty straightforward. The only challenging part is making your units. Let me run over and show this Excel file. I was going to build it, but I don't have time. So I just show it. So escape here. Okay, so 25, the length is given, the diameter 2 inch in feet, the relative roughness calculated, height difference from inlet to outlet, the inlet pressure, efficiency of the motor. A lot of this is just given. And then what I did was I put in 2 lines here, and these 2 lines are for what I'm currently using. And if I want to go with 80 degree, I'll take those and just do a copy and then do a paste, and it's just a little easier for me. Then to keep going, I have the flush, sharp-edged loss coefficient on entrance, 0.5. Standard 90-degree elbows, 0.75. Submerged is 1. Then I have the volumetric flow rate, the area, the velocity. The velocity, notice I leave this because I'm trying to help you here avoid errors. The velocity pressure in these funny units, because if you just throw, hey, it's just 1/2 rho v squared, you're going to get pound mass per foot second squared. But then you convert that to pound force per foot squared using a conversion factor. Then you convert it to PSI, 144 inches squared per foot squared. And now you can almost read this. Oh, it's 2.5 PSI. That's the velocity pressure. It's 2.5 PSI. So we get the friction factor. Notice I calculated the Reynolds number 2 ways. They give the same number. It's just comforting to know I can use 4 m dot over pi d mu for the Reynolds number, or rho v d over mu. So then I calculate the pressure loss for the straight run pipe. How do we do that? Friction factor, length to diameter, times the velocity pressure. We then get the entrance. You can see by the magnitudes that they're pretty small, aren't they? And then there's the sum. So it's almost all that. It's actually 98% of the pressure loss is due to the straight run. Then just kind of wrapping up, keeping going over here. That's the pressure due to the elevation. The pump is going to have to help lift it, and it's 9.86 psi. So the pressure gained from the pump is the sum of the elevation, the rho GH, the friction loss, minus that pressure in the tank at 1, P1. And so the pump has to have the fluid experience an increase in pressure of 319 psi across it. So what's the power? There's a couple powers. What's the power getting into the fluid? Delta P of the fluid that it really sees times the volumetric flow rate. And now that's in foot-pound force per second. You divide by 550 because 550 foot-pound force per second is horsepower. A lot of people, oh, now I know. I'm starting to get back to something familiar. Oh, 36.8 horsepower is minimum. Well, then you have the efficiency of the pump. You use that efficiency of the pump to calculate that I'm going to have to supply a shaft of 49, almost 50 horsepower. Not all that 50 horsepower gets into the fluid, but that's what I'm going to have to supply. And then I'm going to need to purchase power 53 horsepower electrical. So now this was all run with 80 degree oil, right? And I think these numbers are consistent. That one, that one, that one. All I did was copy it. When I want to run with the warmer oil, I'll just grab these two, copy, bring up here, do a paste. And it reruns everything. No, it's supposed to be 200 degree oil, and it's supposed to be 32 and then 42. Oh, it is. Sorry. Thank you. It's embarrassing if you do it wrong. And so the warmer oil, sometimes you'll see people, they'll heat up a fluid to reduce the pumping costs on it. Because the pumping costs, if you're just continuously pushing it, may be small compared to heating it up and dropping its viscosity. So it's a significant, there's a 13% reduction in the power if you pumped warm oil versus cool oil. Well, hopefully that'll help you. I know these problems are challenging. See you next time.